Okay, I think we are going to go ahead and get started. So my name is David Gottfried. I'm the Deputy Director of the National Nanotechnology Coordinated Infrastructure. Welcome to another meeting of the semi-monthly NNCI webinar series, this month focusing on our computation activities. And before I turn it over to my colleague Azad Naimi to introduce our speaker, just a quick announcement. So our next seminar is scheduled for April. So we do not have one in March, but we'll have one on April. I believe it is April 19th, and it will be in the education series. But please check our website, the NNCI website, www.nnci.net, and the events page for updates to that information. If you've missed any previous NNCI webinars, you can view them on our YouTube channel. And I don't have the link for that off the top of my head, but if you just do a search for NNCI in YouTube, I think we're the first link that comes up in a Google search. So, and just a reminder, we will have time for questions and answers at the end of the webinar, and just enter those into the Q&A function of Zoom. And with that, I will turn off my camera and microphone and turn it over to my colleague Azad.
Thank you, David. Hello, everyone. And it's my pleasure today to introduce our distinguished speaker, Professor Evgeny Tsymbal from University of Nebraska-Lincoln. Professor Tsymbal joined UNL in 2002 as associate professor and was promoted to full professor in 2005. And was named Charles Bessey Professor in 2009 and George Holmes University Distinguished Professor in 2013. From 2007 to 2021, he served as the director of an NSF-funded Materials Research Science and Engineering Center. And also from 2013 to 2017, he served as director of the Center for Nanoferroic Devices, which was sponsored by Semiconductor Research Corporation and the National Institute of Science and Technology. Professor Tsymbal's research is focused on predictive modeling of advanced functional materials relevant to nanoelectronics and spintronics. He is co-author of more than 300 papers, review articles, and book chapters. He's also a co-editor of the 3-volume Spintronic Handbook, Spin Transport and Magnetism, which was published in 2019. He's a fellow of the American Physical Society and the Institute of Physics, and a recipient of the UNL's Outstanding Research and Creative Activity Award. With that, I ask Evgeny to please start your presentation.
Thank you, Azad, for your nice introduction. Let me start from thanking the organizers of this workshop for inviting me. So it's my pleasure to make a presentation devoted to antiferromagnetic tunnel junctions and discuss a possibility to control and detect the antiferromagnetic order parameter, which may be very useful for spintronics. So my presentation will consist of 4 parts. So I will start from a very brief introduction, just to introduce the concept of antiferromagnetic spintronics. And then I will discuss antiferromagnetic tunnel junctions based on collinear electrodes, collinear antiferromagnets. So this part of this work was done in my group, and the major contributor to this work was Ding-Fu Shao, who is now professor at Institute of Solid State Physics in Chinese Academy of Sciences, in collaboration with my former students, Gautam Gurung and Ming Li. Gautam is now postdoc at the University of Oxford, and Ming postdoc at the University of Florida. This work was also done in collaboration with Shuhua Zhang from Beijing University of Chemical Technology and Changbom Ong from University of Wisconsin-Madison. So in the third part of my presentation, I'm going to discuss the idea of spin transfer torques in antiferromagnetic tunnel junctions and show that there is a possibility to switch the antiferromagnetic order parameter using these junctions. So this work was also done in collaboration with Ding-Fu Shao and his group in Chinese Academy of Sciences. And finally, in the fourth part of my presentation, I will discuss the concept, same concept of antiferromagnetic tunnel junctions, but now with non-collinear electrodes. And this part of the work was done in partnership with my former postdoc, Zha Zhang, who is now a professor at Shuazhong University of Science and Technology. Okay, so let me start from a few words about antiferromagnetic spintronics. So antiferromagnetic spintronics employs the antiferromagnetic order parameter, which is known as the Néel vector, as a computational state variable, 0 or 1. So we can assign different orientation of the Néel vector depending on state of the antiferromagnet. It could be opposite to original state or rotated at certain angle. So a similar concept can be used for non-collinear antiferromagnets. We can look at different orientations of these antiferromagnets and assign 0 and 1, and even in principle more states are possible in this case, as I will show in my presentation. So the advantages of antiferromagnets against ferromagnets, which are currently used in spintronics, is that they are robust to magnetic perturbations. They have 0 stray fields, which obviously are very important to make memory elements smaller. And probably most important advantage is that they exhibit ultrafast dynamics. If in ferromagnets we can switch the ferromagnetic order magnetization on a time scale of nanoseconds, in antiferromagnets, in principle, it's possible to switch the Néel vector on a scale of 10 picoseconds or something like this. So the disadvantage of the ferromagnet is that it's much harder to control and detect the Néel vector as compared to magnetization in ferromagnets. But recently, there have been some progress along these lines. I'm going to show a couple of examples. So one of the ways to control the Néel vector is to use electric field control. And that has been demonstrated in a certain type of antiferromagnets, which are magnetoelectric. So we can use magnetoelectric effect to switch the Néel vector between opposite orientations by application simultaneously electric and magnetic field. And that was demonstrated in particular for chromium-203, nice publications shown here. Alternatively, we can use ferroelastic strain using piezoelectric substrate, like, for example, in this case, PM and PT. We can apply an external electric field, and this electric field would switch the easy axis. And by switching the easy axis, we can switch the Néel vector. In addition, there have been a few demonstrations of the control of the Néel vector using spin orbit torques. So, for example, in antiferromagnets which have PT symmetry, where P stays for space inversion and T for time reversal, like copper manganese arsenide, for example, one can use Edelstein effect to switch the antiferromagnetic order parameter through staggered field-like torque. I will say more about this in conjunction with the tunnel junctions I will discuss later. Or there have been some demonstrations of switching in different type of antiferromagnets through spin Hall effect, where a heavy metal is adjacent to antiferromagnet and the spin current is passing from this heavy metal. Though I have to say that there have been some discussion regarding these effects in different publications. So Regarding the detection of the Néel vector, so most of the work is done using well-known effect of anisotropic magnetoresistance. In this case, the resistance of antiferromagnet depends on relative orientation of the current in the Néel vector, or analog of AMR, tunneling anisotropic magnetoresistance, where the tunneling current depends on orientation of the Néel vector, like shown here. Recently, also, there have been some interesting demonstration of so-called spin-hole magnetoresistance effect. In this case, antiferromagnet is adjacent to heavy metal, and the spin current flowing through from this heavy metal is partly reflected from the interface, producing additional contribution to the charge current through inverse spin-hole effect. And finally, anomalous Hall effect is a very powerful tool to measure antiferromagnetic order parameter, as was demonstrated in a number of publications. So all these methods, though, have their disadvantages. In particular, in many cases, we are dealing with weak signals and observation of the effects only at low temperature. Anomalous Hall effect may provide rather strong signal, but it's limited by uncompensated antiferromagnets, and also, I mean, it's obviously a powerful tool, but maybe hard to use in device applications because we need three-terminal geometry. So it would be much more beneficial from the point of view of applications in antiferromagnetic spintronics to have something what we have in ferromagnetic spintronics, namely magnetic tunnel junction. This is what we have now, probably the most powerful device so far developed using spintronics, using this approach. So in this case, we are dealing with two ferromagnets which are separated by a tunneling barrier, and depending on relative orientation of ferromagnetic electrodes, the tunneling current may be high, having low resistance then, or low, in this case resistance is high, and this is what is known as tunneling magnetoresistance effect. So this effect can be explained in a simple way using two-spin channel model. So imagine that we have two ferromagnets and same ferromagnets, and this ferromagnet is described by two spin electrons, spin up and spin down, or majority and minority spin electrons. And each of these spin channels have different Fermi surface, like shown here, using this circle. So one Fermi surface is larger than the other. So if you assume now that during the transport process, the spin is conserved, then obviously, because of the larger Fermi surface, conduction for upspin electrons will be much larger as compared to the conduction for downspin electrons. However, if you now flip magnetizations, then we will have a mismatch in the Fermi surfaces. So we'll have then conduction flowing between large Fermi surface and small Fermi surface. And in this case, in both spin channels, the conductance will be low and resistance high. So now the question is, can we do something similar using antiferromagnets? Can we create antiferromagnetic tunnel junction where we have two antiferromagnetic electrodes, and by switching the antiferromagnetic order parameter from parallel to anti-parallel, we can have switching between low and high resistance state. So probably in most common antiferromagnets, it's not easy to achieve because of Kramer spin degeneracy. So all antiferromagnetic metals which have PT symmetry or T1/2 symmetry, where T1/2 stays for half a unit cell translation, must have spin degeneracy. And most of the antiferromagnets we are dealing with have this kind of symmetry. So in this case, we should expect spin-independent conduction, and having this kind of antiferromagnetic tunnel junctions would not be beneficial because in this case, we won't have contrast and the resistance in response to the switching of the Néel reactor. However, recently there have been a lot of discussions about antiferromagnets where these two symmetries are broken. So in this case, we may have what is called momentum-dependent spin splitting. So the Fermi surfaces for two spin channels will be not any longer spin degenerate, and this broken spin degeneracy may lead to spin-dependent conduction. And there have been a number of publications, not complete list is shown here. So in this case, we may have something similar to what we have, in fact, in magnetic tunnel junctions with common ferromagnets. So if you imagine two antiferromagnetic metals, I assume that these are the same type of metals, where the Fermi surfaces have the same area, but not the same in the two-dimensional brilliance zone in K-space. So we have then two conduction channels, spin up and spin down, which are not the same. So in this case, if the Néel vectors of the two antiferromagnets are parallel, we have perfect matching between the Fermi surfaces on the left and right hand side of the tunnel junction, and the conduction should be strong. We should have low resistance. However, if we switch now the antiferromagnetic order parameter, we have a mismatch in the Fermi surfaces, and this mismatch would make much stronger resistance. So basically, the idea of this antiferromagnetic tunnel junction is similar, and the working principle is similar to what we have in magnetic tunnel junctions. So we should have sizable Thermalink magnetoresistance like in MTJs. Now, what kind of antiferromagnets we can use for this? And as an example, I'm going to discuss recently discovered high temperature antiferromagnet ruthenium oxide. So ruthenium dioxide have rutile structure, and it's antiferromagnetic metal above room temperature. It has two sublattices like shown here with ferromagnetic ordering in 001 plane, but antiferromagnetic ordering between the planes. And the Néel vector is pointing along 001 direction. So we have one magnetic sublattice pointing up and another magnetic sublattice pointing down. So what is important is that because of the crystal structure, this antiferromagnet has magnetic space group symmetry, where we have broken PT and T1/2 symmetry. So that means that we should expect to have K-dependent spin splitting. So that means that the band structure will be not any longer spin degenerate at any K point in K space. So indeed, if you do first principles calculations of the electronic band structure of this antiferromagnet, we see that along certain high symmetry lines like gamma X and XM, we have spin degeneracy. And this is because of the glide symmetry shown here. However, along other lines like gamma M, this symmetry is broken because these glide symmetries are not do not hold along this symmetry directions. And we have very large spin splitting. You see that this splitting is about 1 electron volt in this case. So this spin splitting is much stronger than what we may typically have coming from spin orbit interaction. So we don't need to have spin orbit interaction in order to observe this large spin splitting in the band structure of this kind of antiferromagnets. So if you look at the Fermi surface of this antiferromagnet, you have spin up and spin down Fermi surfaces. So they are related by mirror symmetry operations. So they congruent in terms of their shapes, but they're not the same. So the Fermi surface is spin dependent, and that means that the conduction will be also spin dependent in terms of distribution in terms of distribution over momenta in the two-dimensional brilliance zone. So in order to look at this, let us look at the distribution of the conduction channels. So what I do here, I project the Fermi surface, into 001 direction and calculate number of bands which cross the Fermi surface along these directions. So, and this is shown on the left for spin up, and this is for spin down electrons. Again, we see similar distribution related by mirror symmetry operation, but what is important, it's not the same for spin up and spin down electrons. So if we pick up a particular K parallel, particular K point, which contributes to the conduction, we can calculate spin polarization as difference between number of conduction channels normalized to their sum. And we will find that there is a distribution shown here. We have large red and blue contrast here associated with basically perfect spin polarization in this region of the brilliant zone. So obviously, in this case, we should expect that there should be difference in the conduction between parallel and anti-parallel states. So imagine that we have parallel state of antiferromagnet. So what is shown on the left is a left antiferromagnet, and on the right is right antiferromagnet, and top and bottom panels show spin up and spin down. Let's say I pick up a particular K parallel point, and you see that in this case, blue white contrast implies that I have one conduction channel. So I have perfect matching on left and right, and there should be a transmission between these two electrodes. On the other hand, for spin down channel, blue means zero number of conduction channels, and this transmission obviously will not occur because there are no electrons propagating along this line. Now, if you make anti-parallel state, we need to switch up and down spin electrons in the right electrode. And as you can see from this plot, in both cases, we have a mismatch. So we have one conduction channel on the left, but none on the right. Opposite for spin down electrons, we have one normal spin conduction channel on the left and one on the right. So the transmission will be zero in both cases. So we expect much higher transmission for parallel state for this particular K point than for anti-parallel state, which is supposed to be zero. So we should expect then, if we do summation of the whole brilliant zone, we should have parallel transmission to be larger than anti-parallel transmission due to the mismatch in the Fermi surface for anti-parallel state. Now, in order to demonstrate this explicitly, we consider a tunnel junction where we have ruthenium oxide electrodes on both sides, and these electrodes are separated by titanium dioxide, which is a wide band gap insulator. It has nice matching in the base in terms of atomic structure, because both ruthenium oxide and titanium dioxide have ruthyl atomic structure. The lattice mismatch is very small. And also, if you do first principles calculations and find out the position of the Fermi energy, we see that it lies nicely in the nearly the middle of the band gap of titanium oxide. So we should expect tunneling transmission in the calculation. Now, this is what we calculate. So what is shown in these panels on the left and in the right panel is transmission for each K parallel in parallel state of the Néel vectors as shown here for up and down spin electrons. You can see that upspin transmission is mimicking basically distribution of conduction channels on the bottom, and same for downspin transmission. So we have very strong transmission close to the gamma point, and we don't see these features at the corners because the decay rate through titanium oxide for these electrons is much stronger, and we don't have a really big transmission here. Now, if we switch the Néel vector orientation, so we switch it in the right electrode as compared to what we have here, we have anti-parallel state. And because of the mismatch in the conduction channels, we see only very low transmission close to the gamma point. So we see huge difference in the transmission for parallel state and anti-parallel state of this tunnel junction. So if you calculate tunneling magnetoresistance as the difference between transmission for anti-parallel and parallel states normalized to transmission for anti-parallel state, we see the effect as large as 500%. So this is a very big effect, which is quite encouraging and quite exciting, especially because it's in fact comparable to what is known for tunneling magnetoresistance in magnetic tunnel junctions based on iron and G law. So if you calculate, there might be a question whether this TMR is sustainable under applied bias voltage. We didn't calculate explicitly voltage dependence, but we calculated transmission and TMR as a function of the Fermi energy. And we find that there is some reduction in certain energy range, but still, even in this low regime, in this low TMR regime, the TMR is 50%, which is quite sizable value. So we expect that TMR is sustained under applied bias voltage. There is another thing which I would like to mention, because some time ago there has been discussion of antiferromagnetic tunnel junctions in previous publications. But in all these publications, the researchers were looking at antiferromagnets which have spin-degenerate band structure. And basically what they found TMR effects. All these TMR effects were related to what happens at the interface, because in the DFT calculations, typically we have kind of a perfect structure, and there is an alignment of magnetic moments at the interfaces. And that's why we should have, even in the presence of antiferromagnets, we may have some TMR effect. So in our case, this TMR is robust to interface termination. So this is kind of a tunnel junction, which I just discussed before. So at the interfaces, we had magnetic moments being anti-parallel for the case of parallel Néel vectors. So we changed the interface termination in such a way that now this interface termination have parallel magnetic moments for parallel Néel vectors. What we can see, there is some change in the distribution of the conduction. So now there is a large contribution from downspin electrons and small for upspin electrons, but still there is a huge contrast between parallel and anti-parallel state. We see TMR as large as 1000% at the Fermi energy, and there is a similar variation as a function of energy. Also, if you now switch the moments to be again parallel but pointing in the opposite direction for parallel Néel vectors, this picture changes that now we have more contribution from upspin electrons, but again we see huge contrast between parallel and anti-parallel state, and still sizable TMR about 500% at zero at the Fermi, when we calculate at the Fermi energy. So these results are extremely encouraging, and one more comment to make is that we looked at the effect of spin-orbit coupling, because in this case, spin-orbit coupling is supposed to be detrimental. It can mix spin conduction channels and reduce TMR. So this is what we find in terms of electronic band structure in the Fermi surface. So what is shown here in these panels is Z, X, and Y projection of the spin on the Fermi surface. So you can see that X and Y projections are all in green, so it's nearly zero. So the only contribution coming from Z spin as Z, which shows red and blue contrast ranging from 0.5 to minus 0.5, like in case of no spin orbit interaction. And only at the crossing points, and at these points close to the crossing of the bands, there is some splitting of the bands, which makes spin polarization reduced. But this is a small portion of the brilliance zone, so we expect that spin orbit interaction should not contribute significantly to the TMR effect. So now I would like to go on and discuss the possibility of a spin transfer torque using this kind of antiferromagnetic pound junction. So spin transfer torque hopefully is known by those who attending the seminar. Was introduced by Johnson and Luc Berger in 1996, and the idea is that if you pass spin polarized current from ferromagnet in the left electrode, this spin polarization is transferred to the right electrode and produces torque on magnetization, so we can switch magnetization of one of the electrodes through the current. So typically, for the description of spin torques, we are using Landau-Lifshitz Gilbert-Slontsevsky equation, where in addition to the common terms, torque related to effective field, including external field and anisotropy field, and Gilbert damping term, we add two contributions coming from the current. So we have two types of spin torques, known as damping-like torques and spin-like torques. And both torques are scaled with polarization induced by the current. So if you look at the cartoon, how this torques affect the magnetization, we see that damping-like torque is parallel to the damping torque, and field-like torque is parallel, anti-parallel to field-like torque. This is where the name comes from. So basically, the spin polarized current with certain polarization should work in a similar way as magnetic field. And if you calculate magnetization dynamics using a simple single macro spin model, we will see indeed at certain critical value of the current, we can switch magnetization from 1 to -1 along the z direction through dynamics which occurs on a scale of nanoseconds. So this is done by many groups and has been confirmed experimentally in many publications. Now, if you go from ferromagnets to antiferromagnets, we have now complexity coming from the fact that we have now two magnetic sublattices. And these two magnetic sublattices obviously require separate equation, and we have all these quantities which I've discussed before, but different in general on different sublattices which are shown here by index alpha. There is another feature which is important for antiferromagnets, which was not important for ferromagnets, and this is effective field contribution to the effective field coming from the exchange field. So the exchange field matters here because during the magnetization dynamics, these two magnetic orientations may become non-collinear, and then this exchange field torque will be extremely strong because this exchange field is much stronger than the anisotropy field. And this is in fact why we have fast magnetization dynamics in this case. Now, let us imagine that we have current which produces staggered spin polarization on two sublattices, like I've shown in the very beginning when I've discussed, when I've shown example of the switching of antiferromagnets with PT symmetry. So imagine that we have two polarization pointing up and pointing down, affecting P2, affecting sublattice N2, and polarization P1 affecting sublattice N1. So what happens in this case? In this case, if we let us first look at the damping-like torque. So this is what I want to discuss first. So what is going to happen? This spin polarization will produce damping-like torque pointing in the opposite directions. And therefore, we'll have cutting in the opposite direction for two magnetizations, and this torque will not produce magnetization dynamics because there won't be any exchange field-driven torque. So on the other hand, if you have polarization to be the same on the two sublattices, the damping-like torque will be pointing in the same direction, and then it will lead to counting of two magnetic sublattices in the same direction, producing very strong exchange field driven torque, which would produce a rotation of magnetization in XY plane. And this is indeed what you find if you solve this Landau-Lifshitz-Gilbert-Slanchevsky equation using two magnetic sublattices. We see very fast oscillation now on a picosecond time scale, and we see basically a rotation of magnetization. But what is important here is that this rotation will not lead to deterministic switching of the Néel vector. Obviously, if we stop the current, the magnetization will stop somewhere along the z-axis, but it will not be deterministic switching of the Néel vector. Now, let's see what happens if we look at the field-like torque. So field-like torque is basically has a tendency to rotate magnetization around the polarization. Let us again assume that we have staggered spin polarization. We have two polarizations associated with our current affecting sublattice M1 and P2 affecting sublattice M2. Now, in this case, this torques will be shifting, will be rotating magnetization in the same direction. And similar to the previous case, this will produce a very strong exchange field driven torque, and that will rotate this two magnetization sublattices now in ZY plane. But during this rotation, we will have different magnitude of field-like torque depending on position of a particular magnetization with respect to polarization vector. And what is going to happen is that we will see very fast damping of this rotation and very fast switching from positive to negative z direction, as shown in this simulation of magnetization dynamics. So I would like to point here that in order to have this deterministic switching of the Néel vector, we need to have parallel field-like torques on two sublattices. So if our tunnel junction would be able to provide parallel field-like torque on two magnetic sublattices, then if this torque is sufficiently strong, we can have switching of the magnetization of the two sublattices and switching of the Néel vector. So in order to see if this is the case, let me first to discuss the concept of Néel spin currents. So imagine that we have antiferromagnet with two sublattices, let's say A and B sublattices. And let us assume that there is some hopping between atoms in sublattice A, so-called intra-sublattice conduction. So you'll have hopping between up spin electrons and hopping between down spin electrons. Obviously, the current associated with this hopping will be spin polarized because we have exchange splitting of the electronic bands. So we expect that this intra-sublattice conduction should be spin polarized, and there should be spin current associated with this. On the other hand, if we look at the inter-sublattice conduction, where we have hopping between A and B sublattices with opposite spin orientation, then up spin electrons will hop to kind of down spin state, which will be up spin state now. So we'll have now we'll have same contribution for up spin and down spin electrons, and the spin current associated with this will be equal to 0. So now imagine that our antiferromagnet can be represented as current flowing in the same sublattices and current flowing between two sublattices. So if this inter-sublattice conduction will be dominating, then obviously, because the spin current is zero, it will be like having conduction of two resistors with different spin orientation in parallel, and the net spin polarization and the spin polarization associated with each of these sublattices will be equal to zero. However, if we have opposite case, when we have much stronger conduction through magnetic sublattices and smaller, weaker hopping between sublattices, we should expect that while the total spin polarization of the current will be zero, we will have non-zero spin polarization in the current in the two sublattices. And this is what should lead to the staggered spin polarization in these two channels. We can quantify this more explicitly by looking at these currents at different sublattices, and we can define spin polarization in each conduction channel. And I will show result of this calculation in a minute. But what we can conclude that we can have in antiferromagnets, we can have Néel spin currents, which represent staggered spin currents flowing on different magnetic sublattices. And in order to have strong spin currents, strong staggered spin currents, we need to have stronger inter-sublattice hopping as compared to inter-sublattice hopping. And in this case, we should have sizable spin polarization. So it appears that this is indeed the case for ruthenium, titanium, ruthenium oxide antiferromagnetic tunnel junction. So we can look at the conduction channels by looking at the two magnetic sublattices. You can see that if they're stacked in the 001 direction, so along these lines we have basically chains of conduction associated with these two sublattices. And we can have staggered spin polarization associated with the Néel currents. In fact, if you do explicit calculation and calculate spin polarization in these two channels, you will find that it's plus or minus 35%, depending on whether we are traveling along the chain with magnetization pointing up or down. So this is quite sizable spin polarization, and we should expect that there should be staggered spin polarization affecting on two sublattices and associated spin transfer torque. So the spin transfer torque can be calculated using DFT based on non-equilibrium Green's function approach. So here delta rho is current induced density matrix and BXC exchange correlation field. So moreover, this calculation can be done in such a way that we can decompose this contribution to the spin transfer torque onto different sites. And this is what we did here. So what is plotted here is layer resolved spin transfer torque for bias, applied bias of 0.1 volt. So this line here shows the interface between titanium and ruthenium oxide. So this is basically this interface here. So we calculate spin transfer torque on each side, magnetic side and ruthenium oxide. And you see that while the damping-like torque is kind of oscillating, is staggered, at least for two layers near the interface, the field-like torque has same sign. Obviously, this both torques decay very quickly if you go away from the interface. This is similar to what we have in magnetic tunnel junctions, because most of the torque is absorbed close to the interface. Now, if we increase the bias voltage up to 0.6 volt, the contribution to field-like torque is increased dramatically. There's also increase in the damping-like torque, but not as sizable as in this case. And again, we see that the sign of the field-like torque is the same. So that means that we have parallel field-like torques on different sublattices as required for switching of the Néel vector. So the total spin transfer torque can be calculated just by summation of all contributions. So we see significant increase as a function of bias voltage and much smaller contribution from damping-like torque. So based on these calculations, we can expect that this kind of field-like torques can switch the magnetization orientation, because the magnitude of this spin transfer torques is in fact comparable to what has been predicted and experimentally observed for magnetic tunnel junctions based on ferromagnets. So in the remaining 10 minutes of my time, I would like to discuss concept of non-collinear antiferromagnetic tunnel junctions. And for that, I'm going to discuss properties of manganese-3 tin. It's a non-collinear antiferromagnet which has hexagonal structure and magnetic moments which are lying in 0,0,1 plane. So they form a triangular lattice like shown here. Within each plane, the canting of magnetic moments is 120 degrees. So this antiferromagnet has a large Néel temperature, so it's maybe applicable for device applications. So what is important for us that this antiferromagnet has space group symmetry, crystal space group symmetry, such that it supports non-spin-degenerate Fermi surface. So now in this case, the situation is more complicated because we don't have up and down spin electrons. We have all spin projections in the XY plane. So in this case, we need really to project, if you calculate the electronic band structure, we need to project the bands on particular spin components. In our case, it's X and Y components as shown here. So in color, we are showing the magnitude of this projection according to this scale for specific orientation of the Néel vector, which is defined in such a way that it's 0 for this particular configuration of magnetic moments. Now, if we start to rotate the Néel vector, which means we rigidly rotate all the moments by 60 degrees, we see that this contrast, which is shown in this band structure, is changing continuously in such a way that when we go from 0 to 180 degrees, obviously all the moments are flipped, and the red contrast go to blue and blue to red. And in the middle, we have intermediate configurations. I would like to draw attention that these configurations, in fact, are stable configurations because it's also the states at this angles are degenerate. So we can, in principle, have domains with this orientation of the Néel vector. Now, from the perspective of electronic transport, we need to look at what happens at the Fermi surface. So what is shown here is 3 bands, band 1, 2, and 3, which appear at the Fermi surface, which has such a complicated shape. And in color, we again show projection of the spin to X and Y direction. So each of these bands would contribute to the conduction, which in our case will be along the Z direction perpendicular to these planes. So let me look at a particular band. So let me look at band number 1. So what I do here, I'm projecting this Fermi surface to 0,0,1 plane and show what happens in terms of components of the spin in that plane for a particular orientation of the Néel vector. You see that the contrast is changing from blue to red, different from X and Y components. And again, if you start to rotate the Néel vector, we see that this contrast is changing, rotating, and at the end, when we rotate by 180 degrees, it changes completely. So we should expect that if, for example, we have a tunnel junction where on the left-hand side, we have, let's say, this configuration, Néel vector is at 0, whereas on the right, in the right electrode, Néel vector is 180 degrees. We have a complete mismatch between spin orientations in the left and right electrodes, and we should have much higher resistance in this configuration. And this is indeed what we find. So we looked at the antiferromagnetic tunnel junction, assuming for simplicity that we have vacuum barrier layer. So we have on the top manganese 3 tin stacked in 001 direction, same bottom electrode and vacuum spacer layer. And then what we do, we assume that the angle of rotation of the Néel vector, we start from 0, it changes, and then it changes from 0 to 60, and then 120 and 180 degrees, while the angle of the bottom electrode is kept to be the same. So and then we calculate transmission. So again, we have transmission distribution in the two-dimensional brilliance zone, which has a shape of hexagon in this case. So in color, we show magnitude of the transmission in the logarithmic scale. So we have certain regions of high transmission associated with the bands which I've shown before. And now if you rotate the Néel vector, the top electrode, you see that the contrast becomes weaker and weaker, and eventually blue color becomes dominating. So we have much lower transmission in this case as compared to this case. So if you now calculate total conductance based on this transmission, we see sizable decrease in the conduction if you rotate if you change the relative orientation of the Néel vectors, and calculated TMR is again very large, 300%. Again, it's comparable to what we have in ferromagnetic tunnel junction. And this is quite exciting again. We have now very large TMR. And also, in addition to that, we have, in principle, 4 non-volatile resistance states, because each of these states correspond to a particular domain, which in principle can be stabilized, and it can stay as it is, and each of these configurations will have different resistance. Now, when I was invited to make this presentation, and when we submitted these papers for publication, there was no experimental work done in this field, and I was extremely excited that, in fact, last month, a couple of weeks ago, there have been 2 publications in the same issue of Nature journal. So one publication from a group in Japan and another from a group in China, where it was shown that indeed one can have a very large Thermalink magnetoresistance and antiferromagnetic tunnel junction. So let me show results of the work done by the Chinese group. So they used manganese 3 platinum as a non-collinear antiferromagnet, magnesium oxide as the barrier layer, another electrode, manganese 3 platinum. So we have top and bottom electrodes separated by magnesium oxide. And on the bottom, they had collinear antiferromagnet manganese platinum. So this antiferromagnet was used to provide exchange bias. So the exchange bias basically pins the magnetic state of the bottom electrode, and therefore, by applying an external magnetic field, we can change the magnetic state of the top electrode and measure Thermalink magnetoresistance. So what they found is shown here. So you can see if you apply external magnetic field, let's say from positive to negative. So first we see switching of magnetization of the top antiferromagnet. I have to say that this antiferromagnet have some small uncompensated magnetic moment, and basically you can switch the antiferromagnetic order parameter. So you have a hysteresis loop associated with the switching, and then you need to apply stronger field to switch then the pinned magnetic layer shown here. And simultaneously, they measured resistance of this tunnel junction as a function of magnetic field, and you see huge difference by a factor of 2 between state where we have anti-parallel aligned magnetic moments and parallel aligned magnetic moments. And we have this hysteretic behavior associated with the switching. So moreover, they were able to make hundreds of devices using patterning, and looked at the distribution of TMI at room temperature and found that there is a very sizable room temperature TMI, and it's sustainable and reproducible in the range close, the maximum in the range close to 80%, which is extremely exciting development. So at this point, I would like to finish my presentation by saying that we have predicted a sizable and robust Thermalink magnetoresistance effect using room temperature collinear antiferromagnet ruthenium oxide, and also non-collinear antiferromagnet manganese 3 tin, and shown very, very large values of magnetoresistance. So the effect comes from magnetic momentum-dependent spin splitting of the band structure and non-spin-degenerate Fermi surface. Effect of spin-orbit interaction is not important here, and all the effects are coming from the exchange splitting of the antiferromagnets. So we also showed a sizable field-like spin transfer torque in ruthenium oxide-based tunnel junctions, which in our view capable to switch the Néel vector. And finally, I would like to emphasize that it looks like antiferromagnetic tunnel junctions may provide very efficient approach to control and detect the Néel vector in antiferromagnetic spintronics. And obviously, we encourage experimentalists working in this field to look at this phenomena experimentally. So if you would like to learn more about this work, you can look at these publications. So 2 papers are published and 1 is submitted for publication, but you can look at arXiv if you're interested. And finally, thank you very much for your attention.
Thank you very much, Evgeny. This was an amazing presentation, very interesting work, a lot of new possibilities with these antiferromagnetic tunnel junctions. We have a little bit of time, not much, but a little bit of time for questions. So please type your questions in Q&A, and I can ask them from Professor Tsymbal. In the meantime, I have a quick question about the thermal stability of these antiferromagnets. So what is the typical energy barrier for them, and how stable are they compared to ferromagnets?
Okay, so the thermal stability is probably related to anisotropy energy, right? So anisotropy energy typically in antiferromagnets is a bit weaker than in ferromagnets. So, but I think that this question requires a separate investigation because there is not much work done in this field. But yeah, I think I don't have really, good answer to this question. I think this work is just emerging, and I think we need to learn more about this. So it's a good point, obviously, from the point of view of applications, we need to worry about stability and so on. On the other hand, as you know from ferromagnetic tunnel junctions or ferromagnetic spintronics, we don't want to have too strong anisotropy, because in this case we have the too big switching currents. So we should find some balance.
Right.
Again, it's open field for research, so we need to learn more in the future, I hope.
Okay. Yeah. Thank you. So the first question is, can you comment on the sensitivity of the predicted effects, for example, in the case of TMR, to interface compensation in the antiferromagnet? Yeah,
this is what I was trying to mention, that I think it's a valid point, that obviously we never have perfect tunnel junctions. We have never have perfect interfaces. We have always some defects and disorder. So I would expect that this interface, which we assume to be we have magnetization which is pointing in a certain direction, is not like this. We should have some regions where we have magnetization pointing that way, and some regions where magnetization on the right, magnetization pointing that way, and some region where magnetization is pointing that way, and some regions where magnetization is pointing that way. But what we've shown here, that independent on interface termination and independent of what is happening at the interface, we should have, even though we have basically zero net magnetic moment at the interface, we still have very sizable magnetoresistance because the effect is driven by the bulk band structure. So this is what is very important, I think, and this is what distinguishes our work from the previous work, where the effects were computed for PT for antiferromagnets with spin-degenerate band structure, and all the effects were coming from the interfaces.
Thank you. The next question is also related to the interface, but it's about the roughness. Since AFN is at the atomic level, how does the interfacial roughness affect these results?
Yeah, I think I just answered this question. So interface roughness would produce certain regions, and in terms of magnetism, it produces certain regions where you have different orientations of magnetic moments, because our effect is robust with respect to this magnetic moments, we think that in this case, as long as we have certain relative orientation of the Néel vectors in the bulk, we should have very well-defined TMR. It should be stable with respect to interface roughness, and this is one of the points which I would like to emphasize here.
It seems that there are no more questions, and we are, there's one more question. I may have missed it, but how might you expect switching energies for the antiferromagnets to compare to those of ferromagnets? So I guess we just discussed. Well, no, this is about the energy.
Yeah, it's about the energy. So, right. So in the simulation I've shown, so basically the effects are very similar. The effects I've shown in the simulation, I mean, we didn't calculate, obviously, the switching current explicitly, but in the simulation, we see that typically the effects are quite similar to what happens in ferromagnets. So we should expect, in principle, similar current density as compared to ferromagnets. But again, I think that this is maybe too crude statement. We have to learn more about this by exploring explicitly specific type of antiferromagnets and looking at the magnetization dynamics in this antiferromagnets. So my crude answer is that it's qualitatively similar to ferromagnets, but it may be very different if you look at the specific cases.
All right. Thank you so much. We are at the end of the webinar time, and thank you very much for the very insightful presentation.
Thank you.
I'm sure people would reach out to you directly if they have more questions. Thank you.
Yeah, thank you.
Thank you, Azad, and thank you, Professor Tsymbal, and thank all of our attendees who joined the webinar, and we'll see you next time.
Thank you, David. Bye-bye.